Hi friends, once again welcome back in our educational channel, that is Precise Electronics. Friends, in last lecture we had studied T flip-flop, that is toggle flip-flop, and in this video lecture we are going to study new topic, that is resistors. First of all, flip-flop. What is flip-flop? Flip-flop is 1 bit memory cell. It is used to store 1 bit, that is either low or high, that is it is used to store 0 or 1, that is flip-flop. And when the flip-flops are connected to each other to store a large bits, then it is known as a resistors. So group of flip-flops are known as resistors. Suppose this is our flip-flop. So this page is a flip-flop. This is used to draw one figure. So on this paper we are able to draw only one figure. But when these types of pages are connected to each other, when they are binding by using a binding machines, then the resulting device is known as a resistor. Then friend, this is our resistor. In this resistor there are a number of pages, and one page is used to draw one figure. So this is known as a resistor. So what is resistor? The resistor is nothing but a group of flip-flops. And this group of flip-flops are used to store a large number of bits. This resistor has many applications in digital field, digital instrument, digital devices, including in microprocessors. Microprocessor, it is a heart of our electronic, heart of our digital appliances. And this microprocessor, a Pentium microprocessor, which is very famous, that is 8085. So this 8085 microprocessor contains 7 8-bit registers. In that micro 8085, there are 7 8-bit registers, and these registers are known as general purpose registers. It also includes 5 8-bit registers, and these registers are known as flags. So 8085 consists of 7 8-bit registers used as general purpose registers, while 5 8-bit registers are there, and these registers are known as flags. In registers, the data, that means our input, is either entered in serial form or in parallel form. Serial form means 1 bit at a time. Suppose there are number of bits, the 1 bit enters at a time, then it is known as a serial form. But if all the data, all the numbers enters at a time, then it is known as parallel form. The data entered in serial form or entered in parallel form, it is also retrieved. The output is also taken out in serial form or in parallel form. So data can be entered in serial form, one at a time, or all bits at a time, that is the parallel form, and the data can be also retrieved one bit at a time, or the all data can be retrieved at a time. So it is serial output and serial and parallel output. When data is applied in serial form, that means one bit is transferred one after the other, then this data is known as temporal code. What is temporal code? When data is applied in serial form, that is one bit after the another bit, then it is known as a temporal code. And when data is applied in parallel form, means all the numbers, all the bits are stored at a time, then it is known as a spatial code. So in that register there are two types of code, that is a temporal code and spatial code. The registers basically are of 4 types. The registers basically are of 4 types, and these types are depending upon how the data is entered and how that data is retrieved. Means how we are going to feed the data and how we are going to taken out the output, that is retrieved. So how the data is entered and how the data is retrieved. So there are 4 types. The first type is serial input, serial output. That is SISO, serial input, serial output. Second, serial input, parallel output. The inputs are applied in serial form, but we can retrieve the data at a time. So serial input, parallel output. Then the next type is parallel input, serial output. that is a PISO, it is a short form PISO, and the last type is parallel input and parallel output, that is PIPO. So there are four types of register: SISO, serial input serial output; SIPO, serial input parallel output; PISO, parallel input serial output; and PIPO, parallel input parallel. In registers, when data is entered in serial form, that is one bit after the another bit, and the data is also retrieved in serial form, means data is applied in serial form and it is also retrieved in serial form, then this type of registers are known as shift register. What is shift register? A register in which data is shifted in serial form, data is entered in serial form, and data is retrieved also in serial form, then it is known as shift registers. And these bits, the data, are either shifted in left direction or in right direction. And as per the direction of data shifted, there are two types. So as per the direction of bit shifted, data shifted, there are two types: right shift register or left shift register. The first, that is right shift, and second, that is left shift register. And in this video lecture, we are going to study the right shift register. Right shift. So obviously data or bits are moving toward the right hand side. It is known as a right shift register. The logic diagram of right shift register is now going to display on your screen. In that registers, data is applied and that data is shifted from one flip-flop to another flip-flop. So in this case, the data flip-flop, that is D flip-flops, are used. So in this case, there are 4 D flip-flops. Data input, that is the bits, are applied to the first input terminal of first flip-flop, that is a D0. The input applied in this case is 1101, and that input 1101 is applied to the input terminal of first flip-flop, that is D0. Output of first flip-flop drives the input of second flip-flop. Output of first flip-flop, that is Q0. So Q0 is connected to the data input of second flip-flop, that is D1. Output of second flip-flop, that is Q1, drives the data input of third flip-flop, that is D2. Output of third flip-flop drives the data input of fourth, and so on. So in this case, the output of previous flip-flops is connected to the data input of next flip-flop. Then the clock input is applied to all the flip-flops at a time. And in this case, all these D flip-flops are negative edge triggered D flip-flop. Why is negative edge triggered D flip-flop? Because in this case, the bubble is used. So bubble indicates active low, and a triangle is there, and triangle indicates it is an edge trigger. So all these D flip-flops are negative edge triggered D flip-flop, and clock pulse is applied to all the D flip-flops simultaneously. At the same time, there is a clock pulse. There is a clear pulse. Clock pulse is used to synchronize the operation, sequence of operation. And in this case, the clear pulse or reset pulse is used. What is the function of clear or reset pulse? The clear pulse is used to make the flip-flops clear. At the initial stage, the flip-flop is at a random stage. The output is either high or low. But before applying a data pulse, all flip-flops must be in reset mode. So data, the bits stored in all the flip-flops may be 0, 0, 0, 0. And that is achieved by using clear pulse. So the clear pulse, it is the active low clear pulse, because once again there is a bubble. It is active low clear pulse. That means when low clear pulse is applied, all the flip-flops are made clear. So due to which at the initial stage, the reading of register is 0, 0, 0, 0. So before applying any pulse, the flip-flop is in reset. Now friends, data input. What is data input? In this case, it is 1101. this data input is applied to data terminus or input terminal of first flip flop. At the negative edge of the first flip flop, at the negative edge of first clock pulse, at the negative edge of first clock pulse, the data, the bit, that is LSB from the data is shifted in the first flip flop. Initially flip flop is in reset mode and data is applied to the first flip flop. So at the negative edge of the first clock pulse, the LSB from the data is entered in the first flip flop, while the bit stored in the first flip flop is shifted in the second, bit stored in the second shifted in the third, and so on. So at the end of the first clock pulse, the bits stored in the flip flop in the registers are now 1 0 0 0. The 1, that LSB is shifted in the first flip flop, so the bit stored in the first flip flop is high, that is 1. In next flip flop it is 0, next 0 and 0. So the output of register at this stage at the end of the first clock pulse is 1 0 0 0. Next, when the next clock applies at the negative edge of the second clock pulse, the second LSB, now it is 0. Data is 1101. What is the second bit from LSB? It is 0. That 0 is now entered in the first flip. While the bit already stored in the first flip flop, which is already stored, that is 1. So that 1, that high bit is now shifted in the next flip flop, that is the second flip flop. The bit stored in the second flip flop is shifted in the third, and so on. So in this case, the output of register is now 0 1 0 0. 0 from data input is shifted in the first flip flop. The bit stored in the first flip flop is shifted to the second flip flop. The bit stored in the second is shifted to the third, and so on. So at this stage, so at the end of the second clock pulse, the bits stored in the registers are now 0 1 0 0. 0 1 0 0. Next, now the third clock is applied. At the negative edge of the third clock pulse, the negative edge of third clock pulse, the next bit from the data, that is the input, is moved or shifted to the first flip flop, and that bit is high. That is a high 1. So 1 is shifted in the first flip flop. The bit stored in the first flip flop, that is 0, is shifted to the second flip flop. The bit stored in the second flip flop is shifted to the third flip flop, and so on. So once again, in this case, the output is now become 1 0 1 0. The third bit from the data is entered in the first flip flop. The bit stored in the first flip flop shifted to the second. Bit stored in the second flip flop shifted to the third, and so on. So the output at the end of the third clock pulse is now 1 0 1 0. This process remains continuous. That means with every clock pulse, the bit in that data, in the inputs are shifted in the first flip flop. The bits stored in the first shifted to the second, bits stored in the second shifted to the third, and third shifted to the fourth. This process remains continuous. And in this case, the bit is moving toward the right hand side. That's why it is known as right shift register. It is right shift register in which the bits move in this right hand direction. Now we are going to study the clock waveform of this flip flop, of this register. In this case, it is a negative edge trigger. So the clock pulse, that is a negative edge clock pulse, are applied to this on your screen. There are 6 pulses, 1 2 3 4 5 6 7. 5 pulses are there. The data input, that is 1101, is applied to this registers, to the input terminal registers. That is 1101. Initially all flip flops are made clear. So at the initial stage, before applying any clock pulse, the bit stored in this registers is 0 0 0 0. So at the end of the first clock pulse, at the end of the first clock pulse, the LSB from data is shifted to the first flip flop. So due to which in the clock waveform Q0 indicates the high. It goes to high level. The clock pulse, the output of this Q0 is the output of first flip flop. That goes to high level. While the remaining flip flops are remains at the reset mode. So the bits stored on the remaining flip flops are 0, 0, 0. So output at this stage is 0, 0, 0, 1. Or it is 1, 0, 0, 0. When the next clock pulse arrives, at the negative edge of the second clock pulse, the 0 from data is shifted in the first flip flop. So in this clock diagram, the output of the Q0, that is the first flip flop, goes to low level. While the output of second flip flop, that is Q1, goes to high level. While the other two flip flops remains at the same state, 0, 0. So output at this stage is 0, 1, 0, 0. At the next clock pulse, the next bit from the data is shifted. So once again, the output waveform of Q goes to high level, while the low pulse, while the low bit from Q0 is shifted to Q1. So in this clock diagram, the bits are moving in this direction. So it is a right shift register. With every clock pulse, one bit is shifted to right hand side directions. That's why it is known as a right shift register. So from clock diagram, it is clear that with every clock pulse, bit is shifted toward the right side. Now friends, we are going to study the truth table. From the truth table, it is clear that there is a clock input, data input, and the outputs Q0, Q1, Q2, Q3. Data input is 1, 0, 1. Before applying data input, before applying clock input, the all flip flops are made clear. So the output at the initial stage is 0, 0, 0, 0. Now at the first clock pulse, at the negative edge of first clock pulse, the bit LSB, that is 1, is shifted to the first flip flop. So it is given, the direction is given by the right hand side arrow. So arrow indicates that 1 is shifted to first flip flop. So output now goes to 1. Output of first flip flop goes to high level because the input is 1. That first LSB is high. At the same time, the data stored in the first flip flop, that is a Q0, and that is 0. The data already stored is 0, bit is 0. That moves toward the next flip flop. That is given by inclined arrow. The downward arrow is there. The next bit is shifted with the next pulse. So with every clock pulse, the bit is shifted toward the right hand side, and the bit already stored in the previous flip flop is moved toward the next flip flop. So that is a truth table, and in this truth table, the arrow indicates how the bit shifted in the next flip flop, and from this arrow, the working, how this register works, that gets clear. So friend, that is a right shift register. Once again, in this register, the bits or data are shifted in the right side, are shifted toward the right side. That's why it is known as a right shift register. In next lecture, we are going to study the left shift register, in which the bits are shifted in the left side. That's why it is known as a left shift register. So friends, once again, thanks for watching this video lecture. Bye. Take care. Keep watching our video lectures. In next video lecture, we are going to study the left shift register. So friends, once again, thanks. Bye. See you again.